Welcome back. In the previous module, we were looking at first passage times and recurrence times. So, if you recall, we defined, let us say, states for states I and j, we defined Fij of n as the probability that state j occurs in time 1 through n, given we started at state I, right. And similarly, Fjjn is the probability of returning to state j in time 1 through n, given we started in state j, right. Then we said these Fijn and Fjjn are monotonically increasing in n, all right. Therefore, as n tends to infinity, this limit has to exist, right. So, Fjj infinity is the probability, this limit has to exist as n tends to infinity. So, let me just say is defined as a limit n tends to infinity Fjjn, this limit exists since Fjjn is monotonic. This is simply the probability of eventually returning to j starting at j, right. Now, we said that if the probability of eventually returning to j starting at j, if this probability is equal to 1, then we said the state j is recurrent, all right. We said if Fjj infinity is equal to 1, then say state j is said to be recurrent. And if Fjj infinity is something strictly less than 1, then we say, so in this case if Fjj infinity is strictly less than 1, then there is a positive probability of never returning to j having started at j, okay. In this case, state j is said to be transient. All right. So, all of this is just recap from last time. Now, suppose j is a recurrent state, all right. Let us say at time t equal to 0, I start at state j, all right. Then I go through a bunch of transitions and I hit j again at some point, all right. So, if j is recurrent, I will keep coming back to j, right. That is the whole understanding of recurrence, all right. So, what we sort of intuitively argued is that, so let us say j is recurrent. So, let us say this tjj is my first, let us say call it tjj1 to be precise. Tjj1 is the first time I come back to j, all right. This is the first recurrence time of state j, all right. Now, having come back to state j at this point, right, we intuitively argued that the further evolution of the Markov chain here, right, should be statistically identical and independent of whatever happened in this tjj1 interval, right. So, we intuitively argued that this tjj2, the second recurrence time of state j, must be independent because of Markov property of the past and should also be identically distributed to tjj1 because the Markov chain is homogeneous, all right. So, this led us to believe that these instances where if you are starting at j, right, the times at which you hit j constitute a renewal process, right. This is what we intuitively figured out. Now, for a recurrent state j, it turns out to be true and this recurrent and this renewal process of these return times to j will be very useful in studying the long term behavior of countable state Markov chains. However, this intuitive understanding is correct that these TJJs constitute IID random variables, but to prove it rigorously takes a little bit of work. I will tell you why this is the case. So, if you look at this time, alright, TJJ1, the first time of coming to state j, it is a random variable, right. So, this TJJ1 is not a deterministic number. So, for example, so TJJ1, so if I look at probability that x, so x's are the random variables, right. So, I know that x TJJ1 is just j, right. Now, I want to argue that the further evolution of the Markov chain is statistically identical to the Markov chain that started at time 0, right. So, what I want to do is look at TJJ1 plus 1. What is the probability that this is some state k given x TJJ1 equals j, right. Is this equal to question mark, this is a big question mark, all right. Is this equal to TJK, right. See, at TJJ1 I am at state j, right, I have hit j for the first time after I have come back to j. Now, I want to look at the further evolution of the Markov chain in this second, what I want to prove is the second renewal interval, right. So, what is the probability that I go to some state k here, right. So, what is the probability that x TJJ1 plus 1 is equal to k given x TJJ1 is equal to j, right. Is this equal to Pjk, right. Intuitively it seems that this should be true, right. However, please note that this guy TJJ1 is not a number, right, this is a random variable and that itself depends on the previous values of the states of the Markov chain, right. So, TJJ1 is a random variable. So, what you are looking at is you are looking at some sort of a transition probability from j to k, where the index is no longer a deterministic n, right. This is not like p xn plus 1 equals k given xn equals j, right. Here the n itself is TJJ, which is a random variable, correct. So, it is not clear at all, at least it requires a proof that this is the case. It turns out that this is true, all right. It turns out that this is correct, but not clear. This is not clear immediately, right. And the reason that this is true is a non-trivial matter, and this property is known as the Strong Markov property, okay. And that is a subject of today's discussion. This you can view as a little bit of a detour, okay. So, we will use this detour to learn Strong Markov property, which is an important property, and using Strong Markov property we will prove that this is equal to Pjk the way we want it, and then our renewal theory will be usable, okay. You can rigorously argue that TJJ1, TJJ2 etc. are IID, and therefore, we have a renewal process, okay. So, what is this Strong Markov property, right? I have to define this properly. So, this is my digression into, so you can, so this is the detour into Strong Markov property. Okay, or SMP. So, let us say that these xn's, let xn greater than 1 equal greater than 1 be a DTMC on some probability space omega fp, okay. So, all these random variables xn's come from some, so they have to come from some probability space. Let me call this omega fp, right. So far I have not really bothered about what this omega fp is, right. But let, the reason I am doing this is I am going to consider let t be a random variable on omega fp taking values on, so it is a natural number valued random variable. Okay. Let us say taking values on n. Okay. Now, this t, so t could be correlated in some way with these xn's, which is the Markov chain sequence, right. So, what you are given is some probability space omega fp on which this Markov sequence is DTMC xn sequence is defined, alright. I am going to consider some other random variable t, which is a time random variable taking values in n, okay, and this t could be something correlated, it may have something to do with the Markov chain, alright. So, t takes values in 1, 2, 3 dot dot dot, it is a natural number valued random variable defined on the same probability space, and it could be it could have something to do with the process xn that we are considering, alright. For example, this t could be the first time you hit j or something like that, alright. That is the first time the process xn goes to j, alright. Now, question: is it true that probability that x, if you look at x t plus 1 equal to j given x t is equal to I is equal to p I j. So, what am I saying? I am looking at some random variable t, right, which could depend on the process x, right. I am looking at that random t, given that at random instance t x t is equal to I, what is the probability that x t plus 1 equals j? Is it equal to p I j? See, if this t is some deterministic n, then I know that this probability x n plus 1 equals j given x n equals I is simply p I j, right, because the Markov property holds, right. Is it true also for some random variable t which could depend on the process x, right? This is the question we want to answer, okay. The answer generally is no. Okay. Actually, I can ask this even further, right. So, let me refine this question a bit more, okay. Is it true that even Markov property holds, right. So, maybe I should ask, is probability of, so let me just look at this, x t is equal to I and then you know x, let me say x 1 is equal to x 1 dot dot dot, x t minus 1 equals x sorry t minus 1 equals x t minus 1. So, you fix whatever values for states between 1 to t minus 1 and x t is equal to I, okay. Is this equal to probability that x t plus 1 x t plus 1 equals j given x t equals I, right. Is this true, and is this equal to p I j, right. So, this equality, which is I am not saying this is true, all right. In fact, I am saying that this is not true in general. So, this particular equality here is asking whether the Markov property is true at some random time t, right. So, what you have here, this big probability is the probability of x t plus 1 equals j given the entire history, okay. Is it equal to the probability of x t plus 1 j equal to j given just s t equal to I? Is it true? Answer is generally no. And even if that is true, is this equal to the usual transition probability from I to j? Okay. It is not at all clear, right. In fact, the answer is generally no, all right. So, I can show you an example to show that this is not the case, which I will do soon. The strong Markov property is the property that if t is a random variable like so, like defined, and if this property holds, then the random variable t is said to satisfy the strong Markov property, all right. So, let me just show you an example. Let us take this Markov chain 0 1, just a two state Markov chain. This is P, this is Q, 1 minus Q, 1 minus P. This is a very simple Markov chain, all right. Let me define, let us say that I start at x1 equal to 0, I am starting at 0, and you look at t as the largest n such that x n is equal to x n minus 1 is equal to dot 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 x 1 is equal to 0. Okay. So, I am starting at 0 for this Markov chain, simple two state Markov chain, and I am defining t to be the random instant n for which is the largest n for which the first n length run is equal to 0, all right. So, this is my definition of t. So, what does t mean? I want to have, so if t is equal to 13, that means that x 1 through x 13 are all equal to 0 and x 14 must be equal to 1, all right. Then t is equal to 13, okay, that is what this definition means. Let t is equal to, okay. Now, for this t, right. So, can you say, for example, can you look at probability that, what is it, probability that x t plus 1 equals 1 given x t is equal to 0. What is this equal to? This is equal to 1, right. This is by the definition of t, right. This is not equal to going with the probability of going from 0 to 1, right. And in fact, you can argue that, so this is just showing the second part, right. So, for this random variable t, the probability of x t plus 1 equals 1 given x t equal to 0 is not your original Markov chain transition probability, all right. And you can also show that this sort of the first equality also does not hold, this does not have this Markov property at all, okay. So, generally these equalities are not valid, okay. So, bottom line is that if t is a random variable which could be correlated, which could depend on these, which could be dependent, maybe say instead of correlated, let me just say could be dependent, on this x n for n greater than or equal to 1. So, if I have some random variable t which could depend on this process x n, then if I look at whether the Markov property holds for at index t, generally the answer is no, okay. If it happens to hold, then the random variable t is said to satisfy strong Markov property for this DTMC, okay. Definition. So, given a DTMC and a random variable t on the same probability space, definition, T is said to satisfy the strong Markov property if probability that x t plus 1 equals j given x t is equal to I and whole bunch of other histories, that is like x 1 equal to x 1 dot dot dot, x t minus 1 is equal to some x t minus 1 equals p x t plus 1 equals j given x t equals I equals p I j. Okay. So, the DTMC I should say given a DTMC with transition probability matrix p I j. Okay. So, I am given a DTMC with a transition probability matrix p I j. It does not have to be a matrix, it is just transition probabilities p I j, it could be a countably infinite state Markov chains, right. So, maybe I should just say transition probabilities p I j. I want the probability that x t plus 1 equals j given x t equals I and a whole bunch of history should not depend on the other rest of the history, it should only depend on x t equal to I and it should be equal to my original transition probability matrix. I am not saying this is always true. If this is true, then the random variable t, the random time t is said to satisfy the strong Markov property. Okay. Clearly, in the previous example, I showed that the random variable t defined above does not satisfy the strong Markov property, right. So, it is not, it is a special property, it does not always hold, right. So, the big theorem about Markov chains, that is the following theorem. Let t be a stopping time. So, recall what a stopping time is, right. So, we studied stopping times earlier, t be a stopping time for this DTMC, the sequence, then t satisfies the strong Markov property. So, t should be a stopping time, it should be a, it cannot be defective stopping time, okay, it has to be finite with probability 1. So, if t is a stopping time for the Markov chain x n n greater than or equal to 1, so this is your DTMC, then t satisfies the strong Markov property, i.e. probability that x t plus 1 equals j given x t equals I and this whole bunch of history equals probability that x t plus 1 equals j given x t equals I equals p I j. Okay. This is true for all, I mean I should have said this here, for all I j in S and all possible values of x 1, x 2 dot 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 this entire history. Okay. These could be any states in the Markov chain, does not matter what this history is, all right. So, more compactly I can write this as, if I just denote this as some history at time t minus 1, right. So, more compactly I can write this as I want to show that probability that x given x t equals I, h t minus 1 is equal to probability that x t plus 1 equals j given x t equals I should be equal to your original Pij. Okay. So, just to refresh, what is a stopping time, right? T is a stopping time for x1 to xn. That just means that recall T is a stopping time for xn if the event t equals n is a function only of x1, x2 dot 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 xn. So, looking at my first n random variables, I should be able to decide whether I stop at n or not. Okay. More precisely, this t, even t equal to n, must be measurable under the sigma algebra generated by the random variables until time n. So, x1 through xn they generate a sigma algebra, and the event t equal to n must be in the sigma algebra, all right, for all n in n. Okay. So, this is the, if you are used to the sigma algebra language, this is easier to understand. I mean, it's may not be easier to understand, but this is the precise definition, all right. But for all practical purposes, the event t equal to n is determined completely by looking at the first n random variables. Okay. And if that is the case, if t is a stopping time for the discrete time Markov chain, then the strong Markov property holds, all right. Now, we have to prove this proof. Okay. We are looking at, so I am going to write let Hn, so history at time n is defined as I am taking xn is equal to I, and then xn minus 1 equal to little x xn minus 1 dot 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 x1 is equal to little x1, right. So, I am looking at a history at n. Okay. So, we are looking at probability that x t plus 1 equals j given h t, right. So, in h t I have included this h, so it is because of this, so h t is equal to I, right. So, I am taking, by conditioning on this h t, I am looking at x t is equal to I and a whole bunch of history, all right. This is equal to, so I want to prove that this is equal to probability of x t plus 1 equals j given, sorry, x, I want to prove that this is equal to Pij, right. So, that requires some proving. So, this is how it goes. So, this is equal to probability that x t plus 1 equals j intersection h t over p of h t, all right. Now, I am going to use total probability. So, I am going to write the denominator is the same p h t. I am going to look at probability x t plus 1 equals j h t t equals n, okay, and sum over n, okay, sum over all natural numbers n. Now, why is this valid? This is by the law of total probability. I am just using total because t equals n is these are disjoint events, right. If you stop at 13, you are not stopping at 14 or 12, right. Now, this is equal to sum over n probability x t plus 1 equals j given h t t equals n probability h t t is equal to n over probability h t. Okay. This is just by conditioning, definition of conditioning. This is equal to, if I, so I have conditioned on t equal to n, right. So, since I have done that, I can write this as sum over n probability x n plus 1 equals j given h n now t is equal to n probability that probability of h t and intersection t equals n over probability of h t. Now is the crucial step. Okay. If you look at this guy, okay. So, this is condition on h n, right. Remember that h n, for h n I have x n is equal to I, right. So, if I am looking at the probability that x n plus 1 equals j given h n and t equal to n, right. Remember t equal to n is completely a function of x 1 through x n, right, because of the stopping rule property. T equals n is completely determined by x 1 through x n, right. So, I am conditioning on the event h n, which includes all the values from x 1 through x 1 through x n, and in particular x n equals I, and t is equal to n is also completely determined by these random variables, all right. So, bottom line is that this circled event, this can be showed to be circle probability, this can be showed to be equal to probability that x n plus 1 equals j given x n is equal to I, okay. That is because t equal to n is completely determined by this h n, the history h n, okay. So, this is a crucial step, you may want to explicitly write this out. So, that just comes out, right, this guy is nothing but Pij, right. So, this just comes out of the summation Pij times summation n probability h t t equals n over probability h t, all right. H t comma t is equal to n, h t comma t equals. Now, this is equal to 1. Why? Because I mean this is just total probability, right. So, this is equal to Pij as we wanted, right. So, the key step is in realizing that key step is in realizing this, right, that this circled probability is equal to just p x n plus 1 equals j given x n equals y, which is equal to Pij, and this is because t equals n is determined completely by the history h n, right, and in h n we have x n is equal to I is the only thing that matters. So, we can use Markov property, the previous history in h n does not matter, right, for a fixed n. Okay. So, this proves the strong Markov property for stopping rule for Markov chains. Okay. So, this is great, right. So, we moved we have taken this detour, proved strong Markov property, which says that the Markov property holds for stopping rules, stopping times defined from the Markov chain, right. So, if you look at, so detour over, okay, this completes the detour. Now, if you are back to this renewal view of the world, right, you look at, you are back to tjjs and fjjs now, all right. So, you are starting at j, right, and then you are going to a bunch of states, and you are coming back to j, right. This is my Tjj1, correct. Now, you can show that Tjj1, right, which is the minimum of those n's for which x n is equal to j, right, minimum n greater than. So, I am starting at so minimum n greater than 1, I should say, I think, right, minimum n greater than 1 for which x n is equal to j, right. This is a stopping rule. Why? So, because I can determine whether Tjj1 is equal to n by looking at the first n values of the states in the Markov chain. Okay. So, I can look at x1 through xn and decide whether or not Tjj1 is equal to n, meaning that I should have come to j for the first time starting at j, right. So, this can be clearly shown to be a stopping rule, which means that from Tjj1 onwards, the strong Markov property holds. Why? Tjj1 is a stopping time for this Markov chain, and by the strong Markov property, the further evolution of this Markov chain is the same as starting at time 0. Although this Tjj1 is a random variable, it is a stopping time for this Markov chain. So, the statistical evolution is the same as the original Markov chain. Okay. If this Jj1 were not a stopping time, if it were some other crazy random variable like I defined earlier, right, then this may not hold at all, right. I showed you an explicit example where this is not equal to Pij, right. So, you can look at, so if you are going to look at, where did I write that down? So, if you look at this guy, if you go back and look at this, right. I initially said this is not clear, right, but now it is clear that this is true, because Tjj1 is a stopping time, right. In fact, you can now write probability of Tjj1 plus 1 equals k x Tjj1 plus 2 is equal to L given x Tjj1 is equal to j is equal to, the further evolution will be Markovian still, right. The statistics do not change, that is the bottom line. Okay. So, in this now we can argue strong Markov property, we can argue that let us say P, we can argue that P x Tjj1 plus 1 equals k given x Tjj1 equals j is equal to Pjk, Pjk. Right. Not only that, it does not matter how I got to this is equal, this is true, it does not matter. So, these L's whatever however I got to this state j does not matter, right. So, I can in fact just say that probability that x Tjj 1 plus 1 equals k given all the history h Tjj 1, whatever it is, right, this entire history does not matter, is equal to, all that matters is that you landed in j, and then this will be equal to Pjk. Okay. And now the Markov chain evolves like it originally did. It is as though once you have come back to j, it is as though t is equal to 1 all over again, or t equal to 0 or wherever you start, right. So, now we are justified in saying that the further this evolution, right, this Tjj2 is identically distributed, because the transition kernels are exactly the same, and it is independent of due to the strong Markov property, it is independent of the previous states that it visited in getting to j, all right. So, now we can apply then argue tjj1, tjj2 etc. are IID random variables if state j is recurrent, and then there will be renewal every time you return to j will be a renewal instant, and then you can happily apply all the tools we know from renewal theory, key renewal theorem, renewal reward theorem, everything can be applied, all right. Strong law for renewal processes, elementary renewal theorem, all of this will apply, right, if as long as state j is recurrent. So, this module I spent in proving this property, strong Markov property, because it is anyway quite useful, and in particular it this intuitive understanding of this recurrence to state j being a renewal process can be formalized using the strong Markov property. Okay. Thank you. I will stop here.